Hello, everyone. This is Joe Armstrong. Top of the hour here, so open the lines. You can stop hearing the annoying little person saying that it's going to start pretty soon. And we'll just give a minute. Look here and see if people are joining now. So I'm just going to give a minute, and we'll get everybody on there, and then we'll get going here. Let's see. Okay, well, we're in a couple minutes now. Still have quite a few people joining, but let's go ahead and get started. Again, welcome everyone. I'm Joe Armstrong. This is the May version of the Power Systems Virtual User Group webinar series. And this is the second one this month. We had one earlier this month that was IBM specific, but this is a little bit, well, I wouldn't say more general. This one's AIX specific. So we're going to get going with that. Welcome everybody, and hope that you enjoy the show today. Today, no real things to start out with except for what we're going to cover today. So we've got Jaqui Lynch with us, and she's going to talk about AIX Performance Tuning for memory and CPU. And we were talking earlier, Jaqui and I, and if we're lucky, we might get to I/O tuning as well, but that depends on how much time we have. So a little bit about Jaqui. Jaqui Lynch is actually an independent consultant, not an IBMer, one of the few non-IBMers that have spoken for the virtual user group here. And we've had Jaqui on before, so you might have heard of her before. She's got 40 years experience working with projects and operating systems across lots of different vendor platforms, including mainframes, Unix systems, mid-range systems, and even personal computers. She's moved into working primarily on Unix in 1993, and since 1999 has really been focused on Power Systems. So she's been with Power for a long time. She was an IBM customer for 22 years. Then she's worked for a business partner. She's kind of a more independent and business partner oriented today, and focuses on enterprise architecture, virtualization, performance, security, and setting up and delivering Power Systems with AIX Linux, and even does a little bit of IBM stuff as well. So Jaqui speaks at a lot of conferences. In fact, I think I've seen Jaqui conferences since I started going to them 10 years ago. She's a fantastic speaker, and one of the reasons that we like having her to talk to us here at the Virtual User Group. So I'm really happy to have her here. Jaqui, I'll turn it over to you.
Well, thank you, Joe. And I also want to thank everybody for taking the time out to listen to me this morning or afternoon or evening, depending on where you are. So in this presentation, I'm sort of going to start with a little bit of architecture type work. And one of the things I need you to understand is I'm expecting that people have at least a basic understanding of performance tuning and maybe a little bit of experience, because what these slides are, and Nigel had reminded me to say this, is a snapshot of the state of the art. So these have been updated to basically include some of the things that are current as of today. With the way systems are changing and growing, one of the things we're finding is we need to go back and readdress some of our assumptions on things. You'll notice that the agenda, we've got architecting, CPU, memory, some tunables, and then I have IO time permitting. And that's just going to depend how we're doing, because I don't want to go over the 90 minutes. I know how hard it is for you guys to break free. So with that said, let's talk a little about architecting. And one of the first things, I see people go into performance tuning, and when I ask them, well, what are you trying to fix? They don't know. They just know they have a performance problem. So one of the things that I recommend is that you put together a plan, which could be as simple as this, where what is the problem I'm trying to solve? Take measurements of where you're at. We call that a baseline. And this is motherhood and apple pie stuff, but it is really important. Then one of the things I always recommend is when you're doing your baseline, whether you like using Nmon or your own scripts or a combination, also do a perf PMR, because then if you take the stuff when you're running normally and then recreate the problem and get the diagnostic data, then at that point, you actually have really valuable information to give IBM if you have to open a PMR later. All right. And then basically you're going to analyze data. At that point, once you know what the problem is or what it is you're trying to do, then you can document your changes. And I know we all love change control, but you're going to have to document the stuff for that. And also, what do you think is going to happen? And then you make the changes and so on. So this is all motherhood and apple pie. And you notice step 9 says go back to step 3 or go back to step 1. One of the things that it's really important to understand, and you have to get management to understand it, is tuning's an iterative process. You probably won't get it right the first time, but over time and with a plan, you'll usually be able to resolve things. But sometimes you have to go back and do stuff 2, 3, 4 times. And you cannot make all the changes at the same time. That's an absolute guaranteed disaster. So, and I have the comment at the bottom, this might look like common sense, but in an emergency with 6 or 7 VPs standing behind you, the first thing that goes out the window is common sense. So for architecture, I have some things to consider. And I'm going to talk more about these as we go through the presentation, but I want to get them out in front of you. And the first thing is, when you're designing LPARs, there are some things you can do to make them perform better. As an example, if you have an E880, and let's say it's a 48-core single node, you actually have 4 sockets with 12 cores each. So if you can keep your LPARs less than or equal to 12 cores, and you bring things up in the right order, then you have a very good chance that that LPAR will be sitting on a single socket, so you'll get better performance because it's not having to interact with other nodes. On top of that, if you also pay attention to the memory that's actually attached to each socket and keep the profile within that, then you'll also have better memory performance. Now, that's not to say that you shouldn't have more cores than you have in a socket if you need them. All I'm saying is pay attention to the threading and stuff like that so that you can make sure that you're not unnecessarily going over a size. And this kind of leads into the next one. Too many cores and threads. If you're running an LPAR that needs 8 cores when it's running SMT8, and you give it 12 cores running SMT8, you're putting a lot more stress on the hypervisor because it has to manage all the dispatching and everything else for those cores and threads. And we'll talk more about that later. In terms of a bring up order, I'll cover that a little bit later, but we're talking about bringing up your largest LPARs first. Another thing to understand is if you do not fill all the memory DIMMs, and quite often we don't, then when you look at the memory bandwidth numbers that IBM publishes, you will not get those numbers. When those numbers are published, they are published as if all your memory DIMMs are full. So I just wanted to make you aware of that. And then the other thing is understanding the difference in latency between dedicated and shared processor cores. So as an example, when you bring up a dedicated LPAR, each of its virtual processors is mapped directly to a core. And the whole time that LPAR is up, that BP is always mapped to that core. When you bring up a shared processor LPAR, the virtual processors are mapped to whatever core is available when they get dispatched. There's some things the system does to try and help with that, but what it does mean is if the core that shared processor LPAR was running on previously is busy, it may get mapped to a different core, and it may have to wait for somebody else to finish running on that core. So it can take a little bit longer sometimes. And we're not talking minutes, we're talking milliseconds. But if you have a latency sensitive workload, it's something to be aware of. And this last one's really, really important. I see a lot of things out there where somebody says, if you see this, do that. If hypervisor percent is 100%, you have a hypervisor problem. Well, no, if hypervisor percent is 100% and none of the LPARs are doing anything, I don't care. So there really aren't any fast and hard rules about them. What's important is to look at things in context and what other factors are playing in, and then make your decisions based on that. And in terms of helping the hypervisor, this is just talking about, bring up your dedicated partitions first, bring up your VIO servers and your largest shared pool LPARs first, and so on. The other things you got to look at is maximum memory settings. If you set maximum memory too high, as an example, you have an LPAR with 4 gig desired and you give it 128 gig max. Basically, what that does is the system uses that maximum memory setting to determine how much memory is reserved for hypervisor page tables. There is a mapping of real memory to virtual memory, and it always does it based on maximum, not desired, because maximum is as big as you can grow with a DLPAR operation. So if I do that, there's a good chance that I'm going to allocate 2 gigs of hypervisor page tables for my 4 gig LPAR. And by the way, if you're on a large system where you have memory mirroring enabled for the hypervisor, then that's going to be 4 gig you wasted, not 2. So you need to apply common sense to setting those. And then I have just comments about not mixing memory DIMMs of different speeds. That's not so much a problem on the more recent servers because most of them have 1 speed, but it is something to pay attention to. And then I'll touch on this last one more later, but you should never give an LPAR more cores than there are in the box or in the pool. And I'm talking primarily there about the shared processor LPARs. All right. I've talked a little about this, but one of the things that you do want to do is avoid having chips without DIMMs, and you can do it. Now, if I look at an E880 with 512 gig memory, what happens here is it's a 4-socket box, and each socket has some quads assigned to it. With 512 gig, each socket would be given 128 gig of memory, and each socket is 12 cores. So if you keep your LPARs to less than 12 cores and less than 128 gig, then you're not going to cross a socket boundary. As soon as you start crossing socket boundaries, or worse, node boundaries, your memory performance goes downhill. So it's just something to think about. And the reason that it's 128 gig per socket is because IBM has strict rules about how the memory is plugged into the sockets. So if you have 4 sockets and 512 gig, it's going to make you do it. In the case of my 512 gig, 128 gig to each one. Okay, so that's enough about architecture. This, these next couple of slides I'm not going to go over. They're really things to look at in terms of what are the low-hanging fruit to target, and how should you do that. So, a couple of last things to look at. What is it that makes things go slow? And typically, there's the obvious CPU, memory, disk, and network I/O, but there's a lot of not so obvious things. You could have tunables in your system that have been in there for the last 10 years because of a PMR that was opened, and you've since replaced the hardware, you've upgraded the operating system, and nobody readdressed the tunables. There's also a lot of other things that could cause problems. So, don't just assume that it's always going to be the obvious. The other thing you need to understand is what is important to you. Are you all about response time, or are you all about throughput? Because there's a difference. Response time is basically from the time I hit enter, how quickly does it come back? That kind of thing. Versus throughput is how much can I stuff through at a time? So you need to look at those two things and figure out for each of your systems which is the workload you care about. And we call this workload characterization. The next couple of slides are just a couple of fun ones that I'll skip over, but they have to do with having a performance support plan that you go through. So now we're going to talk about CPU. And we're going to start out with dispatching. So we're going to talk about the shared processor pool and the way things get dispatched. Now in the shared processor pool, each LPAR is going to have a virtual processor. Each virtual processor represents a core. And then that virtual processor will have threads associated with it. Depending on whether you're running SMT4 or SMT8, it'll have either 4 or 8 threads. The first time that the virtual processor gets dispatched, it will get dispatched to a core, and that core becomes what we call the home node. What that means is that in the future, it will always try to redispatch it to the same core. All the SMT threads associated with that virtual processor go to the same core. You'll never see the threads for a virtual processor running on a different core to the virtual processor. It just doesn't work that way. That virtual processor will run to the end of its entitlement, and then at the end of its entitlement, if it's got more work to do, it can keep the core if no one else wants it. But if somebody else wants that core, then that virtual processor gets context switched and put on the home node run queue. Then it waits a certain amount of time. If it doesn't get dispatched in a timely manner, whatever that is, it goes into the global run queue and it may end up on a different core. But the point to keep in mind is that its data might still be in the memory on that home node core. So this is how the shared processor pool works. In the dedicated cores, again, we have virtual processors under the cover, but basically it gets dispatched to a core, and that core will continue to run on that one core. So because there is no entitlement. The other thing to keep in mind is that in the shared world, every virtual processor has to get dispatched before one will be redispatched. And this is what gets you in trouble when you put in, let's say you have a pool of 16 cores and you tell the LPAR that it has 17 cores, because at all times, one core is not going to be dispatched. Now, in terms of SMP, as I said, the threads dispatch with the virtual processor. SMT is about throughput. All right. So if you're running SMT4 and you're using all the threads, then you are pushing through more work on average, but you're not going to get as much done in an individual cycle, because with SMT, basically the way it works is that they've duplicated the registers, but they didn't duplicate every register. So there isn't 4 of everything. Now that's changed a little bit in Power 9. They've duplicated more of the registers. So the difference between the SMT levels is different, but certainly with Power 7 and Power 8, the difference was not as, well, with Power 8 it was not as dramatic between SMT4 and SMT8 as it is with Power 9. On Power 7, prior to Power 7, a single thread could actually use 100% of the core. As of Power 7, it can't exceed 65%, and the way that it gets reported on has also changed. So when people first went to Power 7 and Power 8 from Power 6 or Power 5, they would get very upset because they'd come across with the same number of cores and they would be using them, and it would show different busy numbers that was confusing. And the reason for that was in Power 6, the way that it reported utilization was if only one thread was busy, it reported as 100%. If both threads were busy, it reported as 100%. Yet we knew that when you went from using the first thread to actually using the second thread, you got about a 30% kick in performance. So at Power 7, IBM changed the reporting to actually show that. So if you're an SMT2 and you have one thread that's completely busy, it'll show as 70%. And then when the other thread gets busy, it shows as 100%. Right. Then with SMT4, and I actually did some tests to prove these numbers. When one thread's busy, it shows as 63, 77, 88, and then 100 with all 4. And the numbers are a little different on the Power 8, but you get the idea of the fact that it shows different busy numbers. So this change in reporting escaped a lot of people's attention, and a lot of people got very confused, which is one of the reasons that we address this now. So with Power 8, the uplift from SMT2 to 4 is about 30%, 4 to 8 is about 7, and that's what you're seeing over here. I grabbed the late RPerf out of the latest performance stuff. So you can see, if you do the percentages, it's like 45%, 30%, and 7. But if you go down to the Power 9, going from SMT1 to SMT2 is about a 70% improvement, and then another 38 going to 4 and 26 going to SMT8. Now, those aren't guaranteed, it's workload dependent, but it's just something that you should be thinking about. So I would definitely be running at SMT4. I would consider SMT8 if I have something that needs a lot of threads. But when you do that, you want to reduce the virtual processors so that you are actually using the threads. All right, now virtual processor folding is another thing that led to a lot of confusion. With Power 5 and Power 6, we did what we called stacking. So we would kick off the first thread on the virtual processor, and then when that got to about 80%, we'd kick off the second thread. And then when that got to 80%, we would unfold a virtual processor. So on Power 5 and Power 6, you would see a lot of virtual processor folding and unfolding, and you might not see all your virtual processors used. With Power 7, it does it differently. We call this spreading. Basically, it loads the first thread to about 50%, unloads a second virtual processor, kicks off its primary thread. Once all of your virtual processors are being used, then we go back and we use those secondary threads. Once those are all being loaded, we go back and we use tertiaries. So it's not uncommon on a Power 7, if you didn't reduce the number of virtual processors, to, instead of seeing, you know, some of your virtual processors folded, you may see none of them folded, but every primary thread in use. And we call that raw throughput mode. And this was done basically to give you the highest per thread output, throughput. The thing is that it activates more physical cores. And that's one of the, and a lot of people got very confused about this and opened a lot of PMRs because they did not reduce the virtual processors when they moved the workload across. If you need 8 cores to run something on a Power 6, the likelihood that you need 8 cores to run it on a Power 9 is non-existent. So you need to really have a look at those RPerfs and start to reduce things so that you do put the pressure on the threads. And what people saw was that they were using the same number or more cores being used in the Power 7 or Power 8, but they had much higher idle time because they weren't using the secondary and tertiary threads. So just something to think about. And one of the options that you have is that you can go to what we call scaled throughput mode. You can tell it to run in the way that it used to run on the Power 6, but I've got to ask you, why would you buy a Power 8 or a Power 9 and make it run like a Power 6? The right way to deal with it is to appropriately size the virtual processors and the threads. So a little bit more on dispatching, and I stole these diagrams from Nigel. I steal all my best pictures from Nigel. This is an interesting thing to understand about the shared processor pool, and it kind of relates to setting your entitlements properly. I'm a big fan of just because you can doesn't mean you should. So yes, you can set your LPAR to 0.05 of a core and give it a single core for its maximum, or you could set it to 0.1 and set it to 2 cores for its maximum. But if your LPAR on average needs a core to run, then you should give it a core to run as its entitlement. All right. What I see a lot of people doing is they assign things to these tiny cores and without understanding what it does to the dispatch window. So as an example, the dispatch window for a core is 10 milliseconds, unless you've changed it, which hopefully you haven't. So if I give an LPAR a 0.6 of a core as an entitlement, what that means is that it's entitled to a 6 millisecond window. So when I dispatch it, that's what it's going to get. Now, if I have a bunch of LPARs running, and they all are going to get dispatched, sometimes you'll see that they have to be dispatched one after the other. So here I have a single core and a bunch of virtual machines sharing it. So here's my 10 milliseconds, and you can see this light blue guy runs 3 times because every virtual machine gets dispatched before anybody gets redispatched. So here we have the blue, the yellow, the orange, the dark blue, the green, the brown. They all get their entitlement, or they give up the core early. And now the blue one's again because he needs more work. If most of the time this blue guy needs, let's say, 4 milliseconds, and I've given him, an entitlement of 1, then what I'm actually causing it to do is what's happening over here on the right, where the blue one fires up, he gets his cache warm and he runs, and then he has to give up the CPU till all the other guys run. Then he gets redispatched, same process, and then we do it again. And the issue with doing that is that while it's only milliseconds, if you're doing this all the time for those LPARs, you're spending a lot of time getting context switched and getting yourself dispatched and undispatched, and you're going to have more cache misses. So appropriately sizing your entitlement is really important. And that's really what all this is going into here. A 10x or 20x setting for your entitlement is not a good idea. If you only have primary SMT threads, and you can see that in NMON in use, you've got too many virtual processors. And by the way, this applies on dedicated. If you're sitting there and you're looking at a dedicated LPAR and you're seeing lots and lots of cores in use, but only the primary threads, then you want to look at reducing them. So I don't set my entitlements to 10x or 20x. I'm more likely to, I like these average to peak ratios. So I set my VPs to just a little above peak, and I tend to set my entitlement to a little bit more than I need on average, or I might set it to about 0.6 or 0.7 of virtual processors. And it's really important to note that if you are using shared Ethernet adapters, entitlement is really important because SEA is scaled by entitlement, not by virtual processors. So if you skinny down your VIO servers but give them lots of VPs, you're actually going to be hurting your shared Ethernet adapter performance. And by the way, because it's really virtual Ethernet, that applies to your client LPARs too. So just things that you need to be aware of. And again, I mentioned the issue of if you assign too many cores or too many virtual processors to an LPAR and you exceed the number of physical processors or the number of virtual processors in the shared processor pool, then you're going to cause yourself a performance problem because every virtual processor has to be dispatched before the other ones can. And there's a typo here down the bottom. This should say these should not exceed the cores in the pool. I will get that fixed. All right, so a couple of things on avoiding problems. The obvious staying current. There's certain known memory issues. Definitely making sure that your Java is current and get rid of any Java levels that you aren't using. There was some, when we first went to Power 7, and the same applies to Power 8 and Power 9, there were minimum WebSphere and Java levels that were recommended, and that's because they were actually architected to work well with those. And then I have a comment down here that not all workloads run well in the shared processor pool. Most of your workloads, your Oracles, your DB2s, etc., will run very, very well in the shared processor pool. But if you have latency sensitive applications, things like trading systems, things that do polling, certain CPU intensive applications, and I use SAS and some of the high performance computers, as an example, those tend to behave better with dedicated cores. And more recently, I've actually been changing my VIO servers over to dedicated cores as well. All right, so here's an example of what I was talking about with the pool size. So if I run an LPAR stat on my shared processor pool LPAR, some of the things that I'm seeing here are, I've got 72 logical CPUs and I'm an SMT4. So that tells me that I have 18 cores in my LPAR, technically 18 virtual processors, but my pool size is only 17. So what that means is that at all times, I'm going to have one virtual processor that can't be dispatched, and everybody else is going to be waiting for that. So a couple of the other things to note in here, this APP column is the number of physical processors available in the shared processor pool that are not being used right now. You will only see that if you set the allow performance information collection on your LPARs, and you do that by going to the HMC and checking the properties for every LPAR and checking the box that allows it. If you don't allow that, then you won't get the APP information, and you won't get any cross LPAR information. So things like the LPAR column in Nmon and so on. Some other things to look at in here are the virtual context switches. If you start seeing a lot of numbers in here, or it suddenly changes dramatically, then that's an indicator that you are low on entitlement. And these phantom interrupts tend to confuse people. But basically what a phantom interrupt is, I'm running on the core and I hit my entitlement, or for some reason I give up the core. But I had issued an IO beforehand. When that IO completes, it actually comes back to the core that I was running on, but I'm no longer the LPAR that's running there, someone else's. So it says not for me, and that's a phantom interrupt because it's an interrupt that comes in to an LPAR that interrupt is not for. So, you know, don't panic over those unless you start to see them changing dramatically, at which point you're probably going to see much higher virtual context switches because it means that things are getting bumped off the cores a lot. And then this phys-C is your physical cores consumed, and here's your percentage of entitlement. In the shared processor pool world, all I look at for user and system is the ratio between them. I'm not concerned about what they really mean in terms of entitlement and stuff. I look at the phys-C for that. That's really what I'm actually using. But I look at these and if I see 80% system and 10% user, I'm probably going to be pretty concerned, particularly if it's something like an SAP LPAR. If it's a VIO server, then I might look at it a little differently because the VIO pretty much does everything in kernel mode. This is just an example of the same thing for a dedicated LPAR. And here's the one where I was talking about the percent hypervisor. You know, if I'm looking at the percent hypervisor, and as I said, if I see that high, it may not be a problem. Because what it really depends on is what's my user and system. You know, if the system's not doing anything, then I'm not so concerned about the hypervisor. This is another case where context matters. For those of you that are starting to work on some of the systems that allow you to change the frequency the server's running at, which actually changes what the gigahertz is and so on, they've added a new flag to LPAR-stat, this -E, and it will actually tell you if you are running in a power dynamic mode, or in this case it was running disabled, and it will give you the actual and normalized counts, and it will tell you what the gigahertz is. You shouldn't need to look at that, but it's there if you want it. So in the SAR-MU, this is actually a real pain to look at for if you have like 128 logical CPUs or anything like that. But what it will give you is, it will give you the phys-C for the LPARs that are running. And down here you can see the individual threads. So we have 0, 1, 2, 3. This happens to be SMT4. So I can actually do the math and figure out what they're actually all using. And here you can see that the total on it, or the average, because there's an average line it puts down here, was 12.71 phys-C. And this here should be moved over to the left, I apologize. And basically I was at 127% of my entitlement throughout the whole period. So I would look to increase my entitlement. And sometimes you see a capital U line, and that is actually unused LPAR capacity. It just depends. MPstat -S is just going to show you the breakdown across the virtual processors. I put a couple examples in here for you. This is an SMT4 example. This is an SMT8. And again, it just shows you that you're using all the threads in this case. And the same here, I'm using the threads, but you can see that CPU 0 and 1, which are the primary and secondary thread, are busy. 2 and 3, not so much. So this is an example of the summary server for a dedicated LPAR, and you could see the system's running at about 90%. On average, it was 87.1 during the 45 minutes, and it maxed out at 90. So this is a pretty solid, busy system. And I might be looking at, I'd go off and look at the threads and so on and see if I needed to add some core to this. And then this is an example in a shared core world. And again, I've got an entitlement of 1. So my entitlement's up here. I'm not coming close to my entitlement. I'm averaging 0.3. And this is my VIO server. I peaked at 1.1, so I would not increase my entitlement for this. But these are the kind of things that you're going to look at. In the LPAR stat or in the BBBL tab in NMON, this is where it will show you the virtual CPUs and the pool CPUs, so you can compare them there to make sure you're not going over a pool size. And then you can also, if you have the LPAR tab, which you get with that allow performance indicator, you can look at this physical CPU versus entitlement. So here's my unfolded VPs. Like I said, on a Power 7 and Power 8, most likely you will never see anything unfolded unless you've really, really oversized the LPAR. And in this case, you can see my entitlement is 10 and I'm constantly over my entitlement. So again, it's an indicator I need to increase it. Somebody asked the question, what is the acceptable value for virtual context switches on shared storage pool? Sorry, the shared pools. I can't give you a number for that. It's so workload specific. You would have to, this is why I'm a fan of monitor it when things are well, and then notice if things are different. Unfortunately, there are no given numbers for context switches, virtual context switches, or anything, because they're so workload specific. Here again is the same thing for my VIO server. And then this is what I was talking about with the threads. If you look at this one here, this is an SMT4 workload, and you can see that I'm using my primary threads and I'm using my secondaries. I'm not using my threads 3 and 4. In this case here, this is an SMT8 example on a Power 8, and you can see I'm using every thread. This is actually the one that was running at 90%, and in fact, we're looking at adding some cores to this. I've stopped using just VMstat, and I always add the -I-W. And the reason that I do that is it gets rid of some columns that are of no value, and it adds some columns that are valuable. So the columns that it adds are the P column, which is the number of threads that are waiting for I/O messages to raw devices. This new W column, which is basically an indicator of threads that are waiting on direct I/O and concurrent I/O. And I find those useful. And it also adds the page in, page outs, which is real paging, which is where you want to see 0 and 0. Remember, with any stat command, you throw away the first one because that's since boot, and the second one is the interval. The only time I wouldn't throw away the first one is if I'd rebooted within the last day. Here this is the same one that was running at 120% of its entitlement. So you can see that here. And this is also one where my user and system are pretty much equal. And I suspect that's because I'm above my entitlement and I'm having to keep going and asking for entitlement. I'm getting a lot of network questions. I'm actually not going to cover the network in this presentation. We're basically covering CPU and memory and possibly some I/O. And then this R column leads to a lot of confusion. So when you see numbers in the R column, that's your run queue, but it's actually the number of runnable threads. It's actually threads that are already running, as well as ones that are waiting to run. And one of the things you need to keep in mind is that, for instance, the thing that manages all your memory is actually going to be in there. And there's one per memory pool, and we have a lot of memory pools. So it's not uncommon to see numbers in there. It's another one of those ones where you need to actually monitor what you're seeing normally and then see if it changes dramatically. You know, if suddenly your run queue goes from 20 to a couple of hundred, that's a problem. So for instance, with LCPU of 12, I'm not going to be upset if I have a run queue of 12. I am going to be upset if I start to see a run queue of 100. So just things to think about. And this is just an example from my busy server. I apologize for it being fuzzy. But again, my run queue is 56, 88, 83, 71 with 32 logical CPUs. I have tons of free memory. I'm not doing any paging. And the system is, as I said, running at about 90%. So yeah, I would add a core here. and my computational was at 67%. So, all right. This is the shared processor pool monitoring. Again, you have to turn on this allow performance indicator, and Gareth actually answered one of the questions with the actual command for doing that. So I will update the deck and I'll add that command in. Thank you, Gareth. You can look at it, the shared processor pool with that Topaz-C. You can use the P option on Nmon, the LPAR tab in Nmon Analyzer, and there's LP past that as well. This is an example of the Topaz C. Here you can see the pool size is 16 and there's 16 available in the pool. And down here, as I said, for a VIO server, or even actually for your LPAR, monitoring those virtual context switches. And what you're looking for is stuff that changes from what you would see in the normal baseline. And this is the shared processor utilization out of Nmon. So here you can see on my busy system, here's my physical CPU for this LPAR, here's all the other LPARs, and that's what's available in the pool. Okay, so that's what I've got to say about CPU. And somebody made a comment that if the sum of the VPs should not exceed the pool size, is that beating the purpose of the virtualization? No, the purpose of the virtualization is for you to be able to grow to the number of virtual processors you have in your LPAR. If you have a pool that has 16 cores and you have one LPAR that has virtual processors of 17, you're never going to get 17 cores. That pool only has 16. So you're causing yourself a problem. Now you could have, if you wanted, every LPAR in the pool set to virtual processor 16, and they could all grow to 16 if nobody else wants their entitlement. The thing you've got to understand is that when you get your entitlement, you're guaranteed that. So if you have a pool that's 16 cores and everybody has an entitlement of, let's say, 2, and you have 8 LPARs, you have 16 cores already committed. If some of those aren't running, people can grow to their virtual processors. If they are running, then there's and they're busy, then nobody's going to be able to grow. And that's where weights and things like that come in. So there's, overcommitting your virtual processors by basically giving LPARs more than there is in the pool just means that at all times there's a virtual processor or more that's not been dispatched. So we're going to talk about memory. And in the case of memory, I'm going to start with a little bit of basics and then talk a little bit more about looking into this. So there's 2 kinds of memory from the operating system point of view. I'm not going to get into all the shared memory and the operating system stuff. We're just going to talk about the 2 that your client applications care about. There's persistent and there's working storage. Persistent memory is basically backed by file systems. And what that means is that if I need to steal a page, I can just take a piece of persistent memory, and if I need to get it back, I just go get it from the file system. I don't have to page it out or anything like that, unless it got changed. In terms of working storage, this is all your dynamic stuff. It's your executables, your work areas. It's what's going to show up in the AVM or as % computational in your Nmon Analyzer or VMstat. So this is backed by page space. And what that means is if I want to steal a page that is working storage, I have to first page it out, and then I have to page it back in when I want it later. So it's more expensive. The other thing to note is that if % computational is near or greater than 97%, you're going to be paging and you need more memory. I tend to start to get worried about memory when I see % computational getting close to 80%. Because if I have to add memory, it takes time to cut POs and get things ordered and so on if I don't have available memory in the server. All right, we always prefer to steal. Firstly, we prefer not to steal ever, but that life just isn't like that. So if we're going to have to steal memory, we'd prefer to steal from persistent memory because I can always get it back from a file system much less expensively than I get it back from dynamic storage. And there's 5 parameters that affect that: min-perm, max-perm, max-client, LAU file repage, and page steal method. And the last 4 of those are now restricted tunables, and we don't change them. But in AIX version 5, we used to have to change them. And so that's why I want to just cover really quickly what they do. So the rules used to be that what min-perm meant was if your file systems are using less than min-perm, then we would steal from executables. If file systems were using more than max-perm or max-client, we would steal from file systems. And if it was in between, there's a calculation it goes through to figure it out. Then around AIX 5 through TL4, might have been TL5, they brought out this LAU file repage equals 0. What that did was it changed the rules, and basically the rule became simplified. And it was if file systems are using less than min-perm, we'll continue to steal from executables. That's why you'll sometimes see that bump to 5 or something higher to protect things like your SGA. If max-perm, if file systems are using more than min-perm, then it's a strong recommendation to steal from file systems. So, and basically that's to the LAU daemon, which is the daemon that manages all the memory in the memory pools. So what does all this mean? I'm hoping none of you are running AIX 5. In fact, I'm hoping you're not running AIX 6 anymore. Basically, in an AIX 6 or higher system, none of these last 2 should not be set on your system. The thing to note is that max client is a subset of max perm, and it is a hard cap on memory. So if you set that to 20%, you can have available memory and your JFS2 file system can't use it. You don't ever want to do that to yourself. Someone just asked about AIX 433. I seriously hope you're not using it. The whole tuning for 433 is completely different using the VMtune parameters, and I'm not going to cover that here, but if you have a question, you can certainly email me. So basically, these should be set by default, and they should not appear in your next boot. But you should check your HC Tunables next boot, because if you've done any upgrades from like version 5 to 6 or 7, any tunables that were set in the old system will show up in next boot, and they may be wrong and they may be hurting you. And this is what I typically will have in my next boot. I'll typically have settings for min-free and max-free, and those are basically used to determine at what point I start stealing and at what point I stop stealing. We'll talk about that in a minute. I always have some network tunables in there. I'm not going to go into the network, but these are basically the settings that are starting points for a 1 gigabit network. And this RFC 1323 equals 1 needs to be on anytime any of the TCP parameters are greater than 64K, which they are. And then I might be setting min page ahead, read ahead, max page read ahead, and this dynamic pre-buffer allocation, which we'll get into later on, but it's basically the replacement for J2N per pager device, which was what we used to tune JFS2 buffers. This is the new way to tune them. And the default may be fine for you. These 2 here are actually the maximum settings. In terms of page steal method, again, by default, this is set correctly in 6 and 7. And what it does is it actually tells the LAU daemon how to try and steal from file systems. So when your system comes up, the system takes the memory and it splits it across memory pools for the LPAR. There is supposedly a calculation that is total memory divided by 8 equals memory pools. I've brought up 2 LPARs identically sized, and I've had different numbers in memory pools. So I use VMstat-V to find out how many I have. So every memory pool has an LAU daemon, and the purpose of that LAU daemon is to manage that memory pool. It will scan the memory pool looking for free pages to free up when it needs pages. If it's set to 0, it basically scans all the pages. So both your persistent and your dynamic pages are all in one pool. If you have it set to 1, it's going to scan only the file system pages to look for free memory. If it has to, it'll go look at the other ones, but hopefully it fulfills its needs from the file system. So that's what is set in 6 and 7. And to give you an example of what would happen, I've used very simple numbers, but basically I've got 5 memory pools, so I've got 5 LRU daemons, and given that I have 500 gig of memory, each LRU daemon would control about 100 gig of memory. So when I look at this, I've got a 50-50 split. If I have this set to 0, when I'm looking for memory, I'm scanning all 100 gig of memory in every pool. If I have it set to 1, I'm hopefully going to scan just the 50 gig in the file systems pool and get what I need, and then I'm done. So what that does is it reduces the CPU used by scanning, because all that CPU scanning, anytime that it's running around looking for memory, that's using CPU that you can't use for something else. That's going to be kernel time. You combine this with concurrent I/O, and it can make a significant difference in your performance. I'm going to talk real quick about paging. Number one, you have to have enough page space. IBM does deferred paging. What that means is that we don't page until we absolutely have to, and then when we have to, we better have enough page space. Now, in spite of what people will tell you, I think the only exception I ever saw was Sybase, which at one point seemed to be using the page space as a storage medium. But other than that, people will tell you need 2 times, 3 times, whatever it is, memory for page space. No, you don't. You need enough page space to be able to page out things, but you don't need to be able to page out your whole system. So you'll find something that makes sense to you. This system here, I think, had about 400 gig, and it ran, and it was about 25% used because it had a problem with page space buffers. The reason, there can be multiple reasons why that's happening. So if you do start to run into shortages of page space buffers, there's a couple of ways to fix it. The first way is to add another page space. The second way is to swap off one of the page spaces, increase its size, and swap it back on. Third way is to increase the size of the page spaces and reboot. And that's because the number of page spaces is calculated at boot. And the only way that it's going to add more pages is if you add a page space, or if you basically increase the size and either reboot or swap it off and on. Either way, you need to have enough page space to handle anything. And as I said, you don't want a page because paging is bad, but there are some best practices. And the first best practice is have more than one page volume. That way you can page out in parallel. They should all be the same size. HD6 can be like a page bigger if you want. The reason for that is that while it tries to do things in parallel, it also round robins. So if I leave HD6 at 512 meg, and I make everybody else for, say, 16 gig, if HD6 fills up, it's not going to crash the system anymore because we do allow kernel pages outside of root VG. But what's going to happen is every third time it tries to do a page operation out, it's going to hit that one that's full. So now you're not just paging, you just slowed your paging down. So try to make them all the same size. They should be on different disks to each other. And this is a big bugbear in mind with the VIO servers. When the VIO server is delivered and you install it, you get 2 page spaces, HD6 and paging 00. Prior to 2620, HD6 was, I forget which way around it was, 512 meg and paging 00 was 1 gig. After 22620, you now get 2 1 gig files. And the reason this is bad is because particularly with the VIO servers, you're typically booting from internal disks. So if I have 2 page spaces and I'm actually paging, there's a good chance those page spaces are at opposite ends of the disk, and now my CCAM is moving like crazy. The other thing that this affects is queue depth, which is I'm doing paging and I'm trying to get to the volume, and I have to get in the queue for the in-flight IOs, and I've got 2 page data sets on the one disk. So we never ever put 2 page spaces on the same disk. When I bring up a VIO, the first thing that I do is I blow away paging 00 and I make HD6 4 gig. If page spaces are on internal or non-rated disk, you should mirror them. And the reason for mirroring them is because, as I mentioned, kernel pages can now go outside of root VG. So if I'm on a non-mirrored disk and I lose it, I may lose kernel pages, and that's pretty bad. And you don't put it on busy disks. If you've got a page space, one of the worst places you could put it is on your redo logs volume. So these best practices are really to try and keep you out of trouble. The first rule is don't page. But if you have to page, try not to put things in place that will slow down your paging or put you at risk. So that's why I have this slide in here. The SVMon-G allows you to look at memory and what the breakdown is. I use the flag that gives me units because I do not think in pages, I think in megs or gigs. So this is a 512 gig, that should say gig, a gig LPAR. It's using 263, it's got 248 free, 56 is pinned, and so on. And then here it gives you the breakdown between work, persistent, and client. Now here, working in persistent, this is your dynamic, this is your file systems, and this client here is typically your network. So, and then it breaks it down with pages. Things to look at when you're looking for problems, the ls-srad-av command, mpstat-d, and I have some examples of these. These will all help you to look for memory problems. And tprof and gprof you can use for profiling things. So they're all things to look at. So when I look at something like a VMstat-capital I, one of the things I'm going to look at is AVM. And so in this case, my AVM is about 3 gig. What that's telling me is that 9% of my 32 gig is being used for computational. I can also get that in the Enmon analyzer as a percent computational, or I can get it out of the VMstat-v. If you want to know who's using all your page space, you can run svmon like this. It will give you the processes that are using the most page space. And then there's various other, you can ask for just working storage and give it to me in megabytes and so on. You have a lot of different options for that. So someone made the comment that on some critical workloads, more memory for cache file systems help them to have better I/O response. So my comment on that is, yeah, file system caching is very important for certain workloads, but if I get a chance time-wise in this, we're going to cover I/O, and I'll talk a little bit more about asynchronous I/O and concurrent I/O and how those can help you to get better performance. So we've got just a couple of slides with Enmon Memory New tab, and this is just showing you the breakdown of memory between system, processes, and file system cache. And here's my VIO server. So it is not uncommon in an AIX or VIO server to see what looks like 100% memory used when you look at something like an Enmon. And that's because AIX likes to use every piece of memory before it reuses any. So that's not necessarily an indicator that you're in trouble. The indicator that you're in trouble is when you are basically starting to see not enough free memory for you to be able to run the workloads. This is just showing you the percent computational, which is here, and then what my max perm setting is and the num perm. So the stuff below num perm, about 25% of the system is file system caching. And you can see my min perm's down here at 3. So most of this is computational, which is what we like. And that, by the way, was from an app server, an application server, which should be computational. So one of the other things I want to talk about very quickly is Affinity. And what I'm talking about is how memory is assigned to the actual LPAR. So remember I said that if I have like a 4-socket system, I have memory that's within the same chip, memory that's in the same node, memory that's across another node. That's typically with an E870 or an E880. Obviously, if we're running on a core on node 0, it would be really nice to have our memory assigned over there. And this comes back to the whole order that you bring things up, making sure you're on current firmware and so on, to make sure that the system has the best option at bring up time to assign your LPARs in the most efficient way, to make sure that you're not on one node going across to the other node to get your memory. Because when that happens, one of the things that happens is you have much longer latency. And in fact, if you see IBM's performance numbers, what they tell you is they'll give you an inter-node and an intra-node gigabytes per second. And there's a significant difference, because if you stay within a node or within a KEK, then the distance is much shorter that for the access to the memory. So if we look at this is an example from our little S814, so it's a 4U1 socket, and the incredibly meaningful names you're looking for in the MPstat are S3HRD, S4, and S5. So and they're referred to commonly as local, near, and far. So here you can see that 100% of my memory is for the different logical CPUs is attached as close as possible to that logical CPU, which makes sense because it's a single socket system. In this case, this is an E850 with 4 sockets, and again, you can see that some of the threads are 100% with the memory attached to them, and then some of them they're near and far. So this again is with the chip, within the core, within the chip, within the socket. So this is a different socket. This is the same socket, different chip, and this is the same chip. So obviously, whoever threads 78 and 79 are getting dispatched to a different socket, and that can happen. In the case of an E880, this would be, let me get this right, same socket, and different node. I think that's the terminology. So, something like this, where I've only got a few like this, I'm not as worried about. But if I start to see it all over the place, then I'm going to probably start to wonder about whether I had used the correct bring up orders. Somebody just asked what the best Power 8 LPARs that should be SMT8 enabled. Typically, when I'm looking to SMT8 enable things, I'm looking for application servers that can take advantage of it. Some of your web ones, basically multi-threaded things that can take advantage of all the threads. But again, you want to have a look at the workload and see if you're using the threads and determine whether or not you should push down the VPs to force it to use more threads. Okay, so this is a starter set of tunables. We don't really, you don't really care about 5.3 because you're probably not running it, but if you're running 5.3, you would have to set these. For AIX version 6 or 7, the only ones here that you would normally set would be min-free and max-free. All these other ones should be defaulting and should not appear in your next boot file. Now, in order to figure out, sometimes if you have memory problems, you're going to want to look at something like a VMstat-V. Whenever you're looking at any of the stats, you probably want to run an uptime and just see how long the system has been up. The things that the VMstat will tell you are, I have 9 memory pools. It gives me my min-perm, max-perm, and num client, num-perm. Num-perm and num client are the same, which tends to indicate that this is a JFS2 system. I had 66 PBUF blocks. So basically, the way that the virtual memory manager works is when I get an IO request, it gets put into a PBUF while I build the IO request. After that, I determine what kind of IO it is. Is it a page space one? Okay, I need a page space buffer for that. Is it a JFS one? Okay, I need a JFS buffer for that. Is it a client? Then I need like a network one. I need NFS or Veritas. And then the other one for file system buffers is JFS2, and there I use something called external pager file system IOs. So I basically put it in one of those buffers, and then I can start to do things like send it out to the IO subsystem or whatever. So this is a healthy system. It's been up 39 days. There's not a lot of blockages, so I'm not worried. And by the way, it is not uncommon on a system that has no JFS file systems, they're all JFS2 or RAW, to see anywhere between 1400 and about 2048 file system IOs blocked for the JFS. I have no idea why, but I see it on every system. So, and it never changes. So I don't worry about it. And that's the thing about these is you want to run one and then maybe run one a couple of hours later and see if they're changing, because obviously what you're interested in is not what it was for the last 100 days when you don't know when it happened, but what's happening now. So this next one is a very unhealthy system. So about close to half the system is being used for file system caching. Here you can see I've got pbuff problems, I've got page space problems, and I've got, what is that, 39, almost 40 million IOs blocked with no file system buffers. Out the right here, I've sort of put an indicator of what the solutions might be to fix them. So, and one of the things to keep in mind is that when you have blockage at one place, it's likely that you're going to have blockages at other places. So as an example, if I can't get any file system buffers, then the IOs that I built are going to stay in the pbuffs. So if I'm not able to get those IOs out to file system buffers and out to the system, then it's highly likely that the application that is trying to issue those IOs is going to get blocked, and it will probably get paged out. So sometimes those three go hand in hand, and when you look at it, it's not just a pbuff problem, you've got to solve all three. And sometimes just solving the pbuffs and the file system buffers reduces the pressure on the page space buffers. So, another example of why context matters. So in this case here, you have to look at how long the system's been up. If it's been up for 2 years, you have no idea when this happened. If it's been up for a week, then I wouldn't like these numbers. So I'd run the VMstat-V in the morning, and maybe 3, 4, 8 hours later, I'd run them again and see if I've got a rate change going on. And then I would fix them. All right, so here's my pbuffs. So when I run the LVMO, it gives me, by default, just root VG. And what it tells me is what for this volume group is my block count. And then it gives me a global block count. So you can see root VG is just fine. And what these pbuffs are is the number of pbuffs per HDisk in that volume group. We used to tune these globally. We now tune that. That is no longer supported, and in fact is restricted. We now tune them by volume group. Because why would you give a volume, because these are pinned memory buffers, why would you give a volume group buffers that it's not going to use? So now we go through, we look at every volume group, and we look at what the block is for it. And you can see that it was the SAS volume group, which happened to have SAS work in it, which is pretty heavy IO. And so we changed it to give 2048 pbuffs per HDisk. And that resolved the problem for the pbuffs. But just be aware that we now do this by volume group, which to me makes a lot more sense. Now, the other thing to watch out for is when you're trying to figure out if you have enough free memory, and you look at the free column. So you need to understand the relationship between memory pools, min free and max free, and the free column. So if I set min free to 960, which is the default, that says that, well, the old way that it used to work was, if I'm using more than max free, if I have more than max free pages free, then I'm not really going to run around page stealing. If I have somewhere between min free and max free of pages free, then I'm going to steal pages until I build myself up to above max free. And then if I'm below min free, I'm pretty much page stealing all the time, and I'm probably thrashing. So what people didn't understand, because it sort of came in later, is that that's a relationship that also has to include the number of memory pools. So what you have to do is min free and max free apply per memory pool. So if I have one memory pool, then these numbers are fine. But if I have 10 memory pools, then what that means is I have to take that 9902 and I have to divide it by 10, and I get 990.2. So actually, per memory pool, I only have 990 pages free. So I am right between min free and max free, and I'm page stealing, and I'm not that far off thrashing. So, and you may not see much in the page in, page out until things get really bad. So just be aware that you have to take into account here the number of memory pools before you compare it to min-free and max-free. And you may want to actually bump up your min-free and max-free. And there's a calculation that I use for that. There's lots of calculations around, and sometimes IBM will give you a recommendation to use much larger numbers. I've seen people with 20,000 pages free, and really what they're trying to do is they're trying to buy themselves time to recover memory. So I typically do a calculation where I basically take them whatever min-free is set to, and I calculate what the minimum it should be is, and then I take the maximum of, usually it's J2 max page read ahead because I'm JFS2 times logical CPUs, divide by memory pools, and that gets me a number. So I never make min-free less than 960. In fact, I usually round it to 1024 because I like IBM magic numbers. And if max-free came in at 1472, I'm probably going to bump it to 1536 or 2048. I talked to Grover, and one of the recommendations he made was that the difference between them shouldn't be more than around 1,000 unless IBM support tells you to make it more than 1,000. That way you're not spending all your time managing a lot of this memory. If you over allocate this, you could see really high values in the free column, and you're going to be paging because what you've done is you've said, well, unless there's 22,000 pages free, I'm going to page. So just be a little aware of going crazy with these numbers. And like I said, if you think you need more, I'd open a PMR and just say, what should the values really be for this workload, which means you need to take a perf PMR for them. This is an example, as I said, of what your next boot might look like. You could have different numbers here. The default here is 128. The default here, I think, is 16, and that basically pre-allocates JFS2 buffers. If you get to the point where you've got 256 here and you've maxed it out and you can't go any higher and you are getting JFS2 buffer shortages, you will need to open a PMR with IBM to determine what the next step is. There is another parameter that can be set, but it is a restricted parameter, so you don't want to go changing that unless IBM tells you to. All right, so we have about 15 minutes or so left. So I'm going to try to really quickly cover I/O. Somebody just asked, how do you determine the number of memory pools to create, and how does AIX determine how many? Supposedly, AIX there is actually a parameter in VMO where you can change this, but AIX supposedly divides by 8, and that's how many memory pools it creates. However, I have never ever had that necessarily match, because I think there's some other things it takes in. I've never created the memory pools myself. I'm not even sure you can. So I typically just run VMstat-V after the LPAR is out and make a note of how many I have. All right, we're going to try to really quickly cover some things relating to I/O. And we're going to start with a rough anatomy of what happens when you do an I/O. And I kind of covered this before. The LVM requests a PBUF. Then we actually take that I/O request and we put it into a file system buffer of some kind. So it could be a file system client or the JFS2 external pager, or it could be a page space buffer. Then that gets queued to an HDisk. That's what we refer to when we're talking about queue depth. Queue depth is actually the in-flight I/Os for an HDisk. Then it gets queued to an adapter, so your fiber adapter or your vSCSI adapter, and then it finally goes out to the disk subsystem. Now, additionally, about every 60 seconds, there's something called the sync daemon, and if you're just running regular JFS2, that'll run every 60 seconds, and its purpose is to run through memory and flush out any dirty I/O to the file system. So if you've modified pages in memory, about every 60 seconds, those get written out. And I always, used to wonder why they always told me after I changed the root password to do sync semicolon sync. Well, one of the reasons is that forces the sync daemon to run and write that stuff out to the file systems, to the operating system. Although I always felt that if I couldn't remember what the password was I put in 60 seconds ago, there's probably a problem. But that does run every 60 seconds. And that's why it's not uncommon to see bursts of page outs, where it's actually on a busy I/O system, where it's basically taking pages in memory that are file system that have been updated and writing them out to the file system. All right. I want to touch on I/O wait because, again, it's something that people get very confused about. I/O wait is not necessarily useful, and the reason is that it's very misleading. If I look at this, I have 7 threads. I don't know what happened to my 8th one. And you'll notice that 3 of them are red because they're blocked and 4 of them are running. So 3/7 of my threads are blocked. This will show as 0% I/O wait, because what I/O wait is a measure of idle time. All right, how many times is a core idle waiting for an I/O to complete? But if something's running on that core, it doesn't show as idle. So the fact that you see no I/O wait does not mean that you have I/O wait. Again, if I have the reverse and I have, one thread blocked and nobody's waiting for any cores and nothing's running anywhere, I'm going to see a number that's not necessarily meaningful either. So the thing to learn from this is I/O wait's a measure of idle time. How often was a CPU idle and there's at least one I/O still outstanding? So it's not that it means nothing, but it does mean that you can't absolutely trust it as an indicator that you have an I/O bottleneck or that you do not have one. Because the CPU that's in an I/O wait state can still run threads if there's any that want to run. Some of the basics, you can do all the tuning in the world you want. Data layout will have more impact than some of the tunables. If somebody, I spend a lot of time planning layout. I actually literally sit down when we order a server, I map out which adapter goes in which slot so that I get the best advantage from the adapter slots up. I fight tooth and nail when people try to give me 1 HBA for my high performance data. And you'd be shocked how often somebody wants to give me 2 terabyte LUNs because they've got an amazing disk subsystem that has gazillions of gigs of cache. And so it's performing really well. So all I need is 1 LUN. No, I don't like larger LUN sizes because number one, that they typically mean that I'm going to have larger PP sizes, which is not good if I have a lot of little file systems. It also means if I have 1 LUN for everything for Oracle or DB2, how do I separate out my redo logs and my data and my high performing things? And the next question is, well, why do you care about that? Well, it's all about queuing. All right. I have a queue depth setting for my LUNs, and the maximum I can set that to depends on the disk vendor. So if I have a queue depth of, let's just say 20, what that means is that individual HDisk can only have 20 outstanding IOs at a time. So if you give me a 2 terabyte LUN to run everything on, and I can only have 20 outstanding IOs at a time, you're never going to see a disk performance problem in your storage subsystem because I can't send you more than 20 IOs at a time. Now give me that 20 terabytes in, let's say 200 gig LUNs. So now I've got 10 of them. And now I can actually push things. So now all of the multi-path drivers enforce this. They won't put more than queue depth IOs to an HDisk. And most of the multi-path drivers, if you install them, which you should, where possible, will set the queue depth. Whether or not you need to increase the queue depth is dependent on the performance that you're seeing. So sometimes the default queue depth is enough. Sometimes it isn't. Depends on your disk, your IO workload and so on. And for those of you that are doing MPIO, I don't have a slide in here on it, but IBM is recommending that we move now from STD PCM to the new AIX PCM that has come out as part of the most recent versions of AIX. I will try to add a link to the end of this presentation to some of the white papers that are out there on that. But if you just do a search on AIX MPIO or AIX PCM, you should be able to find those. So some additional things on queue depth. As I said, what I'm talking about is the in-flight queues. And it's basically that in-service queue and it's not going to let you go over it. The other thing that's interesting is if you actually attach a HDisk, if you attach a disk subsystem that AIX doesn't know what it is, so you end up with other SCSI, I have typically found that it enforces a queue depth of 1 no matter what you put. So you do want to make sure that you have the correct drivers loaded for whatever the disk subsystem is, so that it shows as a NetApp or an IBM or whatever it is, so that you know that the system recognizes it and will honor the queue depth that you set. And there's maximums that you can set for queue depth depending on your vendor. Some vendors don't like you to go to the maximum. Some vendors recommend that you do. I would not go to the maximum unless I have an issue that needs to be addressed with queue depth. But it's really up to you. We're going to talk about HBAs. HBAs are impacted by num command elms and also a max transfer size. And at one point you could bump them up on both the VIO servers and the client. Then they changed it so that you limited the clients, and now they've changed it again so that you're not limited. So we'll get into that in a minute. If you run an IOStat-DL, you'll see the service queue full down on the right-hand side. That is no longer a count of how often it was full. It's actually a rate of the IO submitted to a full queue. So they actually change what that means. So 2.1, I'm not so worried about, but if you start to see large numbers in here, this is an indicator that you want to increase your queue depth. And there's a number of different ways to look at it. There's the RDTL flag, there's SAR-D, NMON-D, so on. Or you can do an IOStat-DL. Now for the adapter queues, that's a whole nother area. If you run an fcstat command, there's 3 things you're going to be looking at: number of DMA resource counts, no adapter elements count, and no command resource count. So if the DMA is the direct memory access that's used for IO, if you see numbers in there, that's when you would adjust this max transfer size. And the no command elements and the no command resources is the num command elms. Num command elms is actually queue depth for the adapter. If you are using NPIV, make your changes to your VIO server and reboot the VIO before you change the clients. When I say reboot, so because the VIO must be the largest. So if you want to use 2048 on a client or 1024 on a client, you must have the VIO server be at least that big and have been rebooted. If you don't do that, what will happen is there's a very good chance, well, the LPAR won't boot until you fix the VIO. So just be aware of that. And to show you the numbers in here, here's the max transfer size. By default, that's an 8 meg DMA, or sorry, 16 meg DMA. I usually by default bump it. I change this to a 2, and that way I get a 128 meg DMA. There was a level of AIX, I think it was 61TL2. The virtual fiber clients would always use a 128 meg DMA no matter what you put. If you left it at the 100,000, so I change it for consistency anyway. And then again, as I said, at 71TL2, 61TL8, they put a limit in of 256 for the num command elms. That got lifted depending on which one of these TLs you were at. You can actually go back to the higher levels if you want to. What you're supposed to do is add up the number of IOs you want to have outstanding for each of your LPARs, and that's what your VIO server should have for num command elms. The reality is you're going to have to check with your disk vendor what they'll support, and typically it's going to be 1024 or 2048. So one other thing is with the HBA max transfer size, the size of the DMA you get depends on the value you put in. So the default's the 16 meg. Whether you put a 2, a 4, or an 8, you get 128 meg. And then if you add a 0 to the 1, depending on the bus that you're running, you'll either get 256 or 128, and then there's some various flavors of it. I just got this answer from IBM just in the last week or so, because there was a lot of confusion over max transfer size. So I wanted to put this slide in so that you had it. Now, if you're trying to figure out what you should put num-command alums to, one of the things you can do is run the fcstat minus capital D command and look at each of the 5 ports, and what you'll see is a high water mark of active commands and of pending commands, and then you'll have your no adapter elements count and so on. So here what I'm seeing is 616, I can't do math, is the minimum that I'm going to need to be able to run this workload, because that's my actives and my pendings. And these pendings are what leads to this no adapter elements count. So this gives you an idea of like the minimum you need. Me, I'd just make that 1024. And just a couple of other things on tunables. So we talked about pbuffs, and you need to use the LVMO command to change those. You may end up having to change J2 page max page read ahead. What that is if I determine that a workload is sequential, how many pages ahead do I want to pre-read? And that gets turned on if you use stuff like concurrent IO, and then this is the new buffer tuning. Some other interesting tunables that you can take advantage of for IO, there's the no A time. Be very careful using this, but basically, if you have files like redo logs and archive logs, /temp, SAS work, you don't actually care the last time you read or touched a file. You'd always care about the last time you changed it or when you built it and so on, but you really don't care for a redo log or an archive log the last time you read it. This can save you significant IOs from recording this stuff. So you can actually change that so that it's an option on the file system when it mounts, and you don't actually, and it doesn't record the access time. You would not do this on your production data. Log equals null is another one that I typically turn on for SAS work and temp. And basically what that says is do not keep JFS2 logs for this file system. And the JFS2 log just caches the last, I think it's 64 entries of metadata. You don't want to turn that on for any file system you care about, but for temp space, you might want to think about it. I'm going to skip over these, but FileMon is a way that you can actually run traces on your files. It does use trace, so you will get a performance hit. But the sort of thing it will look at is what's busiest used physical volumes and logical volumes. So here's the most active logical volumes. Here's my most active physical volumes. And you may use this to determine whether you need to rebalance workloads. All right, we're going to do a quick touch on asynchronous and concurrent IO. So asynchronous IO basically means that the server can kick off some IO and go off and do something else while it's waiting for that IO to happen. And it applies to both raw IO and file systems. And I can tell you that Oracle and DB2 love it. So it's something that you definitely, if you have applications that could take advantage of it, you definitely want to tweak and make sure that they're actually taking advantage of it. If you have the things change with version 6, basically if you do a pstat now, what you see is a POSIX pool and a legacy pool. And I can tell you that Oracle and DB2 use legacy pools. So there are definitely not going to see, like you used to see, all the AIO servers that were sitting around in the system. If the system's really busy, you might see them, but typically no. Now the max servers value is per logical CPU. So if I have 10 logical CPUs and I set max servers to 30, I will get 300 of these. And that's the one that you're going to grow as you need to. Sometimes people will bump min servers up to a bit closer, and one of the reasons they do that is because they don't want to be spinning up and shutting down asynchronous IO servers on a busy system. So they bump min servers up so that we're not doing that as much. In Nmon, there's a proc AIO tab, and basically this is how many are currently running, and I think the AIO prox is the maximum that it saw during that time. So you can actually see it that way. There's also various other commands. IOstat has a -A flag and so on. Now, direct IO and concurrent IO basically allow you to resolve something that we call the double buffering issue. If you're running something like a database, and I'll use Oracle as an example, file systems get read into memory, and then they get copied into the Oracle application space. They get updated in the Oracle application space, they get copied back to the memory, and then they get pulled out to the file system. We call that double buffering because it's basically the same data in two places. So with direct IO, which came out with JFS and has been around since 5.1, it's also what you get in Linux. I basically say, you know what, just copy it straight into the application space. Just put it straight there. Don't do this double copying stuff. It reduces your LRU daemon and sync daemon overhead to nothing. It gets rid of the double buffering, and that double buffering uses both CPU and memory, so you're freeing up memory and you're freeing up CPU. There are some things about DIO where it doesn't like the compressed file systems and so on, but the reads are asynchronous. The thing you give up is file system read ahead, so this is not a good thing for a heavily sequential workload because it gets rid of file system caching. It just says, just come straight into the application buffers. Now, concurrent IO is only an AIX, and it's only for JFS2, but it is built on top of DIO, and it's what gets you the performance that's close to raw devices. So a lot of people moved away from raw devices into JFS2 because they could use concurrent IO. The key thing to note, you've still got the same limitations in terms of you don't get file system read ahead and so on. You do get the memory and CPU savings. However, you have to be using it with an application that enforces write serialization at the application, because basically it does not lock the inode during writes. So if the inode's not locked during writes, then two people could write to the same thing and break it. So that's why you typically only use concurrent IO where an application understands concurrent IO. So places I typically see it used, and I'll use Oracle as an example, database files, redo logs, control files, flashback files, but never for things like binaries or archive log files, things like that. So somebody just asked why I would not use no A time for production data. One of the reasons I would not use that is because I will absolutely fail an audit. When the auditors start looking at things, they want to know every time the file was accessed. They don't care about temp, they don't care about SAS work, but they definitely care about your production data. So that's one of the reasons I wouldn't turn on no A time on production data. One other thing that you may see is these things called demoted IOs. And typically I see this with Oracle, but what it means is that somebody has, in their application, has done a write that is not aligned to the file system block size. So the application may be deciding to write 512 byte or 1K byte blocks, but the file system has a 4K block. I see this with redo logs a lot because Oracle writes those as 512 byte blocks. What ends up happening is I go to do the write, the block size doesn't match, so it ends up redoing the IO, and we call that a demoted IO. They use a lot of kernel CPU and they cause a lot of physical IO. I've put in here for a JFS2 system how to find them, and if you see them, you need to figure out what the issue is. All right. Well, I'm actually
we're wrapping up here. Yeah.
Yeah, I'm going to actually skip through the flash cache. I'll flip through that and just go to, the tips to keep out of trouble, which is monitoring your error reports, checking your performance APARs. I mean, this is all the motherhood and apple pie stuff. I tell people, go read the firmware history, because if you're back level on firmware, go read these firmware histories, and it will actually tell you all the things that change in the different firmware levels. And then you can actually figure out whether the problem that you have is fixed in the firmware level that you should be going to. And my last couple of things are taking a baseline, documentation, and then if you haven't found out by now, if you have the 512 disks and you add 4K disks, you cannot mix them in a volume group. So when you're trying to migrate root VGs and so on, this is where alternate disk copy is your best friend, because it's going to, you can basically alt disk copy from a 512 to a 4K disk, but what you can't do is put them in the same volume group. As ever, use Nmon for your monitoring. I run at 724. Also use the AIX Performance Advisor. And that is everything that I have. And I'm sorry I had to skip over the flash cache stuff, but the material is in there. So thank you very much for your time. And thanks, Joe, for organizing these. Really appreciate it.
Well, thank you, Jackie. They're only successful because of speakers like you. And the presentation materials are out on the wiki, and you can download them from there. And I will be putting a replay out there later after I get it all set up and downloaded and put back up on YouTube and all that kind of stuff. So hopefully I can get to that today. So with that, thanks again, Jackie. Just awesome job. Just so much great material. And really appreciate you taking the time to present this for us. Any questions that come up, if they come to me, I'll route them to you. Okay?
Yeah, no problem.
All right, very good. Everybody, the next webinar is end of June. Actually, we're going to have two of them the end of June, I hope. We'll do another sort of IBMI specific one and another one that's either more AIX or else kind of general. I'm not sure what the topic's going to be yet, but look for those invites. And with that, hope you all have a great month and that your summer is starting out strong.
Yeah, thank you.